Hello and welcome to Explaining Rasterizer, a series of lectures where we try to understand how Rasterizer works one subsystem at a time. Today is an exciting point uh, because last time we fully covered everything that there was to syntax trees and parsing. Well, everything except manipulating and mutating syntax trees. That's going to be covered differently, but everything we need to actually analyze the source code. So today it is the first time we actually dive into the guts of a compiler, into that horrible middle end, which exists between the parser, which interacts with the source code, and the IDE layer, which takes internal analysis information, processes it, and spits out various completions, go to definitions, highlighting, and all that stuff. Here are the dragons, because I think we understand relatively well how to engineer the compiler frontend, although in the details the syntax trees might not be perfect, but the general API, the overall feel of it, it's really great. I really love it. We also understand relatively well how to provide an IDE, although that horrible main loop in the LSP server binary is very hard to understand, but still it's like there is like a reason for that complexity. It's like does exactly what it is supposed to do, and in general the IDE APIs are pretty solid. However, the stuff in the middle is pretty much a research project right now. Stuff works. It isn't pretty. So the amount of times I will be looking with an amazement at the source code and exclaiming like, what the hell is going on here? I don't understand here, will be much larger since this point where we start looking into the internal implementation. So what I want to discuss first is the general notion of IDs and how we get from purely syntactic constructs to entities inside the compiler which denote semantic things. How we go from syntax of a structure to a notion of a structure entity which lives in a namespace, which has names, which has child entities like fields. But unfortunately, to do that, we need to discuss macro expansion first, because the way entities get their identity is primarily through their location in the source code, and entities might be located in the macro expanded file. So to cover this basic location, we need to cover macro expansion. I do not want to focus on macro expansion specifically, as that is probably one of the least interesting and also the most hacky aspects of this middle end, which is itself hacky. But we need to kind of like understand macro expansion as a black box to understand how we actually add macro expansion files into the notion of data our compiler works with. And yeah, I guess that is really the core. So actually, let's start looking at the source code. If you recall, I've said that all the input to the database is stored in this base DB crate over here, and specifically in this source database crate. And really, the amount of ground state is like really tiny. It's just a set of files with their texts and the crate graph, which describes the logical structure of crates and dependencies between them. And this model is easy. So you like have a file ID. This file has a text. You can parse this text into IST. So now we know what IST source file is. And yeah, here we go. The problem is when you add macro expansion into the picture, macro expansion starts to sort of create pseudo files. So you get not only what was originally written in the source code, but also files which are a result of macro expansion. And accounting for that requires quite a bit of bookkeeping and logic to handle. So, how does macro expansion works? What is the interface between parser and macro expander? And the answer to that question is token trees. So let me actually just too many crates. Really, Rasterizer should be a smaller project. ABC. Yes, I guess at this point I should have just like found the crate by name, but here we go. So yeah, token trees. Token trees are defined in TT crate, and they describe the interface to macros. Basically, token trees is what macros in Rust Analyzer consume as input and emit as output. And token tree is a relatively simple thing. It is, well, either a leaf or a subtree. And subtree is a bunch of token trees with a delimiter, where delimiter is either parenthesis, brace, or bracket, or a leaf. And leaf is your literal, like 92 or hello. All those things are literals. Punctuation, so things like colons, how do you call it? No, this is a colon and this is comma, always mix them up. Braces, hashes, well, no, braces are not punctuation, that's important. Braces are inherently a part of subtree. So literals, punctuation, and identifiers, which are things like hello or async or async. And yeah, the way there is no special leaf for keywords. Keywords are actually just identifier at this level. So this token tree thing originates in Rust C, and it like plays several roles in the compiler with varying degrees of success. And kind of like the question is, why do we even need a syntax tree? And for that, let's look at the example of macro. And let's actually use some example from the test. Yeah, so let me copy paste this outside of the test so that syntax highlighting is not confused. Yeah, so this is like example of macro, and it allows us to emit a bunch of from impulse. And the syntax for invoking the macro looks like this. You say the name of a macro or a path to the macro, then you say bank, and then you spell parentheses, any of the three kinds, and the stuff inside. And the rule here is that the stuff inside must be a correct parenthesis sequence. So braces, round parentheses, and square brackets must all be matched exactly. And that, like, the reason for that is rather good and rather fundamental. We want to be able to parse syntax without actually expanding macros. We do not want to be macro expansion and parsing completely intertwined. So here we understand that this impl from's macro invocation ends here, simply because we can look at the balanced parenthesis sequence without deeply understanding what is happening inside this macro. This is great because, well, it allows, well, it basically allows us parsing the stuff. And that is kind of like a thing which Rust got from Lisp in that, that kind of like Lisp looks like this. So there's like just parentheses and as expressions. No our syntax, no our punctuation. And the benefit of such Lisp syntax is not homogeneity, which is often claimed, not like the property that you can use a data structure to represent Lisp syntax. That's kind of just like not really, like it's not really unique. You can use Rust data structure to represent Rust syntax, or you can use JavaScript JSON to describe JavaScript syntax. It's like, well, kind of like, yes, like code as data, and you can manipulate code as data in any language, and like you absolutely do not have to have this as expression based concrete syntax for this, although it does make this like marginally better because everything is uniform. The crucial bit about as expressions and Lisp is that it allows you to have macros, because when you have an X expression, you understand where the macro ends without necessarily understanding what this macro means. So here, like in the Lisp, I don't know. Yeah, I haven't wrote any Lisp in like years, so cannot come up with a philosophical example. But like, let's suppose like this is Lisp, and that like this is a macro. And in Lisp, we understand that the input to this macro is the stuff inside these parentheses. So again, we don't basically we don't even have a question where what is macro invocation, what is outside macro invocation, because everything is super strict tree in the surface level. In Rust, we don't have this in general. Our free-form syntax is like this, and if say we kind of like didn't have any specific rules to delimit macros, so let's say we allowed to write like stuff like this, like I don't know, then it like would be impossible in the parser to understand where this macro ends, because well, kind of like, is this like semicolon the end of macro, or maybe it's like the part of the syntax or whatnot. By having these delimiters, macro boundaries are set up correctly. So that's kind of like the first role of the syntax tree, of the token tree, is that we formally say that the input to macro is a balanced sequence of tokens. The second reason for token trees to exist is that we, at least kind of like aspirationally, don't want macros to like re-implement the parsing, and we don't want macros to be completely different in their look and feel from Rust. So we say, hey, instead of parsing a raw string into macro, I'm going to tokenize the stuff in Rust and parse a sequence of Rust tokens, so that a macro can implement arbitrary syntax as long as it uses Rust tokens. And the idea here is that, well, if like tokens are good for Rust-C, then tokens would be good for macros as well. This didn't pan out splendidly well. We kind of like have this model where macros operates on tokens, but this kind of like model is like there mostly for backwards compatibility and not because it's like some objective reality. Because turns out that Rust tokens are not enough for Rust compiler. And as a simple example, you cannot distinguish between two angle brackets and a shift left operator without a parser. So the way parser works is that it's kind of like ask the Lexer to emit two tokens, and then depending on the context, it either glues or doesn't glue the tokens. And obviously, like your macros do not really have this context about the tokens. Another fun example where we clearly see that the token model like isn't objective reality is things like x 0.1.0. So in today's Rust, this actually is a field access. It is parsed like this, x 0.0 and then 0.1. But it is lexed like this. It is lexed like identifier, then dot, and then float and point number. And the way Rust works around this is that in the parser it just splits out this floating point token into constituent parts. So like you see that there like isn't such well-defined thing as a token. There is no strict layering between lexical level and syntax level. They are intertwined, and like sometimes parser goes into the lexem level and actually tweaks the stuff. So this idea that tokens are like a good universal language isn't like really great. Oh, like another example, macros in Rust cannot absorb white space, but some people want to write macros which are actually aware of white space so that you can write like Python in Rust macro. And that is kind of like one of the desires to stabilize proc macro API to actually get access to token positions so that you can infer the white space by looking at the positions of two adjacent non-white space tokens. And that kind of like shows that like this like model of tokens is like a wishful thinking. It's like very strange. But there is crucially, and yeah, kind of like in this sense, it would probably be a simpler model to say that hey, like, macro just gets a string as an input. But there's a crucial twist here, and the twist is hygiene. Rust macros are hygienic. Or hygienic, I don't know how to pronounce it. But that means that basically if you have, let's actually create an example. So let's have a macro which says that x equals 1, and then we have a function x equal 2, and then we will call a macro, and then we will print x. So if I understand Rust correctly, this should print 1. This should print 2. Exactly. Yeah, so let's write it this way. Yeah. So it's like we first define 1 and then we define 2. And the reason for that is that like Rust is hygienic and it understands that this x refers to this x, despite those two having the same name. And you notice that we haven't yet implemented hygiene Rust analyzer. So when I press go to definition, on this x actually get to the macro. So that's kind of like something which we need to fix about. Anyway, so the point is that you want your macros to be hygienic, and you want to somehow make sure that this x and this x are different. And that means that you need to stop this hygiene information somewhere so that it is actually present in the input of macro and in the output of a macro. And the place where we stuff this hygiene information is tokens. So tokens are a carrier of hygiene, and that turns out to be pretty important for the way macros in Rust works. So now we understand like motivation about tokens. I guess it also makes sense to like talk about like the general implementation thing. So again, like the original bright idea was that we architecture our compiler, our language as a series of independent phases. First, we start with source text. And then we split source text into tokens and make sure that parameters are balanced. So what we produce is not just the tokens, but actually token trees. Yes, that's, I guess, something I haven't explicitly said, but that's the important high-level bit, that token trees are essentially just like a sequences of tokens, except that they are not the sequences, they are trees because parameters are also balanced. So that's kind of like very rough data structure, very low level data structure, almost as like there's like very little between a raw stream of tokens and a token tree. So the idea is like you start with text, and then you produce this token tree, and then you build your syntax tree out of token trees. That's not what happened. So both in Rust-C and in Rasterizer, token trees, syntax trees or ISDs aren't actually built of those tokens. Because as I've explained, kind of like parser kind of like needs to bend this definition of token and come up with tokens out of thin air to make stuff works ergonomically. What's more, tokens inside procedural macros and tokens inside macro by example and tokens inside Rust-C are actually kind of all different in a sense that from the point of view of a macro by example or declarative macro, this is one token, so it is will be matched against like this. Actually, let's do some experiments here. So let's define macro which takes a single token and emits. Oh, that's okay. Yep, you see, so if we parse something which is not a token, we get an error here. If we parse a token, okay. Why is it curious? Yeah, I wouldn't expect this to actually expand. Let's maybe add an extra branch here. Okay, yeah, so we can now, I guess, okay. So yeah, now we can like use this tiny macro to check what are the tokens. And you see that like stuff like plus plus is many tokens, but stuff like shift left is one token. But if there is a space there, there's like many tokens. So one, many. But for plus plus is kind of like many and many. So kind of like declarative macros like to think about tokens which are glued. And that's different from procedural macros, because procedural macros will always look at even this as two tokens. So turns out that kind of like token trees are not actually a universal model. It's not like the actual stuff Rust is made of. It's just like a specific backwards compatible shim which exists between compiler and macros to make macros behave. So with that in mind, let's look at the actual implementation of tokens in Rasterizer. So first of all, yeah, like token tree is a tree of leaves and subtrees. And subtrees carries delimiters, and that's really, there is like all to this thing. It's like just a stupid data structure. You see that tokens also carry IDs. Like each token has an identity, so like literal has ID, and that is kind of like a half-baked attempt to support hygiene. And turns out that like tokens don't actually have IDs, so it's like it was like something I kind of like invented and thought as a good idea, and it like took me only like 3 years to realize that hey, kind of like that doesn't make sense, and Rust tokens do not work like this. So kind of like just ignore IDs mostly. But yeah, the rough idea behind IDs was like to allow tracking how the tokens go through macro to understand the resulting hygiene. Okay, so how do we actually yeah, and like yeah, that's a simple data structure, but it is completely unrelated to the syntax trees. So there's like no imports from syntax here. You see that there's like no dependencies in cargo tumble. So how do we get like this data structure from our actual syntax, which is defined in the syntax crate, and how do we feed this into the macros? For that, again, like we have like many kinds of macros. We have declarative macros, we have procedural macros, and we also have like built-in macros. And we will look at the declarative macros as an example. Okay. Again, we won't be looking at the implementation. We will be looking only at the interface. And the primary thing we'll be looking here is syntax breach. So as the name implies, it is a thing which exists to breach from syntax to token trees and from token trees to syntax. And this is like a primary method here. We take a syntax node and we get a subtree. That's actually let's write a simple smoke test here. Understand what are we talking about? So let's source file parse. I don't know. Let's say that we have like this file. And let's extract macro call out of it. Not unzip and find map, not filter map. Unwrap. So let's look if this works. And also let's print it this way as well. Okay, so we got our macro call. What is okay? Seems like we actually changed the way display implementation works. Not accustomed to that. Okay, so this is like our macro call, and here is like this syntax tree for it. And you notice that, yeah, actually, you notice that it has like token tree as a child, and we can actually look at this token tree. So token tree is this thing, and it is parsed as well a bunch of syntax nodes, and like these are IST token trees. So these are from syntax. These are not from the TT crate. And we can actually convert this to Tata using Okay, let's call it syntax there, and then TTTT will be syntax node to token trees. Yeah. So that's the text of a syntax node. That is how this part looks like in terms of syntax. And this is what we get when we convert it to TT token tree. As you see, the things which change here is first we get rid of white space, so the thing is significantly more compact. Then we assign IDs to stuff. So 1, 2, 3, 4, 5, 6 are IDs of the tokens. And then we also, with each punctuation character, we also carry a compressed information about white space, basically a single bit indicating whether an next punctuation character is adjacent to the current one or if there is a space between them. And that's exactly what can be used to determine if it is a shift left or to adjacent less than signs. Okay. Second part of return value here, token map, is a mapping built on top of token IDs, which allows us to understand which tokens in the original syntax tree corresponds to tokens in the subtree and back. So basically what we get here is we convert a data structure into sort of like an isomorphic data structure together with bidirectional mapping between the two. Okay. And actually, well, we have here we can go in the opposite direction. We can go from token tree as entity and get back a syntax node. But the kind of like wrinkle here is that syntax nodes are structured. It is not like just arbitrary syntax. It is either expression syntax or a type syntax or an item syntax or whatever. While token trees are unstructured. So when we convert from tokens to syntax tree, we essentially parse it, and we need to specify what kind of things are we parsing here. So to get back to our example, let's say we have, is there something genuinely ambiguous we can write here? I don't really think that there is. Okay, let's start with a simple example. So to syntax node, and we use our TT, and for parser entry point, we use items. Let's unwrap this. Again, we get both a tree and a token map to understand the relationship between the tokens. And now let's print syntax struct. Oh, it's node, I think. Yes, syntax node. Because again, this thing returns parse, so it's a pair of syntax node and bunch of parsing errors we get in the process of getting this node. Let's run this. Oh wow, no compilation errors. Oh right, because there are like curly braces there. Can I? Okay, let's parse it as a block then. Okay, yeah, that makes more sense. So let's look what happened here. We start with this syntax. And this thing is a token tree. So although it looks like a struct declaration, struct s semicolon, in fact, this is just like a bunch of tokens. Without knowing what this macro does, we cannot like a priori understand that this is struct. And depending on this macro, like this might be just some macro which accepts arbitrary tokens and emits nothing. So like there's absolutely no guarantee that this is a struct. Then we convert this into token tree with a curly brace subtree and a bunch of stuff. And then we parse this subtree back into syntax tree, and we ask the parser to parse this as a block expression. So yeah, and block expression we need because there is like curly braces here. And what we back here is, well, block expression, which contains a single statement, which is an item definition of a struct. Okay, splendid. So this I think is like a rather interesting distinction between RASC and Rasterizer in that RASC at least started in the model where syntax nodes are made of token trees, while in Rasterizer token trees are completely separate layer specifically for macros, and you can convert a syntax tree to a token tree, or you can get back from a token tree to a syntax tree. And you only need this for macros. So I guess with this, we can look at the overall workflow for a macro. And I guess for that, it makes sense to start with a test we looked at previously. So this is the test. It defines a macro, and that invokes a macro, and it asserts that this macro invocation actually expanded to this thing. How does it happen? So first, you parse with macro rules, and by the way, syntactically macro rules looks like a macro invocation. So again, like this thing here is essentially a token tree. So first you parse macro rules, and then you process its macro definition to compile these macro rules into a valid macro. Then you parse with macro invocation. You realize that this refers actually to the macro we've seen before. Then you take this argument of a macro invocation, which is a syntax, convert it to a token tree using syntax node to token tree. You feed this token tree into the macro invocation. It does its magic and spits out a new token tree, and then you parse this token tree as a bunch of items to give you this result. So let's look now in terms of the implementation. Again, to reiterate, syntax tree, syntax bridge, where we have syntax node to token tree, and token tree to syntax node. Then here in the macro by example root file, we have macro rules definition. Macro rules definition can be parsed from a token tree. And as a result, you either get, well, a well-formed macro rules or an error. And yeah, in general, in Rasterizer, we never ever want to return results. We always want to give some fallback, but macro expansion is one place where it is particularly tricky to do robust and resilient error recovery. So here, I don't claim that this is like the best way to do it. I think like we should and must actually do better here. But like today, like anything which is at least remotely workable, because yeah, it's just a giant pile of complexity. So we didn't want to implement like the perfect error recovery and macro expansion engine ever. We wanted to have at least something which works, because it's like a huge unsolved problem. Okay, so yeah, I've made the font bigger, but that actually makes it harder to look at two things side by side. So let us try. So again, macro definition. In macro definition, the thing to the right is actually a token tree. So you see this is like token tree which doesn't have any structure. So when we are processing this macro definition, we take this token tree and we call syntax node to token tree to convert from syntax node to token tree. Then we call macro rules parse with this token tree to get macro rules. Then we call syntax node to token tree on this token tree to get token tree corresponding to macro argument of this macro. And then we call expand, and we give our macro one token tree and get back another token tree. Again, like this expand results tries to be like better in terms of error resilience, but by not too much. And yeah, the problem here is it contains like an optional error instead of like vector of errors, because there might be many errors anyway. Like everything needs to be rewritten, everything needs to be refactored. Okay, so we expanded and got back another token tree. And using that result, we call syntax node to we called token tree to syntax node to go from TT subtree to a syntax node. And this gives us back this nice syntax tree with froms. I guess we can actually look at it as a syntax tree by using this magic declaration MBE smoke test. Okay, is it gonna work? Yeah. So you see, I've asked the test to also print the actual syntax tree we get, and you see that hey, we have like a macro items which contains two impls. So that's like the first impl, and somewhere here is the second impl. And yes, you see like syntax trees are actually that complicated and that verbose. And yeah, I guess that's it for today's lecture. So to reiterate, well, one more thing. Do I want to cover it? Do I not want to cover it? Yeah, I guess I do want to cover it, because that's touches what we looked at previously. In the second tree, the syntax node, we need to take TT and parse syntax node. And this is exactly where our generic infrastructure for tree sinks and token sources comes into play. So if you recall, when you're describing parser, I said that, hey, we made parser abstracted over source of tokens. And this is exactly what we are taking advantage of in this place. Here, we use these TT tokens and not the actual tokens made of text as an input to the parser. And the parser just doesn't care. It does its thing, it parses the stuff. So now, conclusion. In Rasterizer, syntax trees and token trees are various distinct layers. And in particular, token tree is architectured as a boundary between macros and everything else. So when you want to interact with a macro expansion, you want to start with a syntax, convert it to a token tree, run macro expansion on this token tree representation, and then get a syntax tree back. And yeah, that's actually like the whole tweet. That's what this lecture was all about, in that when we will be looking at the macro expansion interface next time, there will be this step where we go between syntax trees and token trees in one way to get macro argument, and in another direction to parse the result of macro expansion. So yeah, I guess that's it for today. Thank you for watching and listening. See you next time. Goodbye.